This page gives us a visual representation of the trade-offs we've been discussing with thermal noise. It starts by simplifying our signal-to-noise ratio, or SNR, calculation. The formula shown assumes we can ignore most other noise sources and focus on just two main ones: the quantization noise, which is inherent to the number of bits, and the thermal noise from the switches, which we model as KT/C. Now, let's look at the two graphs. They both plot SNR in decibels against capacitance. The x-axis, capacitance, is on a logarithmic scale, going from very small, 0.1 picofarads, to larger values, 1 nanofarad. The different colored lines represent ADCs with different resolutions, from 8-bit all the way up to 16-bit. What's the first thing you notice in both graphs? As the capacitance increases, as we move from left to right, the SNR for every resolution goes up. This makes perfect sense, right? Because thermal noise is KT/C, it's inversely proportional to capacitance. So, if we use a bigger capacitor, the C value is larger, making the thermal noise smaller. Less noise means a better SNR. But then, look at what happens at the higher capacitance values. The curves start to flatten out. Why do you think that is? Well, once the capacitance is large enough, the KT/C thermal noise becomes so small that it's insignificant compared to the other noise term, the quantization noise Qn. At this point, the ADC's performance is no longer limited by thermal noise. It's limited by its own resolution. The SNR hits a ceiling determined by the number of bits. You can see the 12-bit ADC plateaus around 74 dB, and the 14-bit one levels off around 86 dB. Pushing for even larger capacitors beyond this point gives you diminishing returns. Now, let's compare the two graphs. The one on the left is for a full-scale signal swing of 2 volts, while the one on the right is for 1 volt. For any given capacitance and resolution, the SNR is higher in the 2-volt graph. This is because the signal power is proportional to the square of the voltage swing. By doubling the input signal swing, we quadruple the signal power, which gives us a significant boost in SNR. This is another important lever we can pull in ADC design to improve performance. So, what's the big picture here? These graphs beautifully illustrate the challenge of designing high-resolution ADCs. If you want a 16-bit ADC, which has the potential for a very high SNR of around 98 dB, you can't get there with small capacitors. With a small capacitor, the thermal noise completely dominates and your 16-bit ADC performs no better than a 12-bit or even a 10-bit one. To unlock the potential of that high resolution, you are forced to use larger capacitors to push the thermal noise floor down below the quantization noise floor. And as we learned on the previous page, larger capacitors cost more chip area, can slow down the circuit, and may consume more power. This is the fundamental trade-off.